Characteristics of optical detectors is the topic of this lecture. We know that optical detectors are very important in optical communication system because in optical communication system light travels in the form of light, and when it is received at the receiving end at the optical or using optical detector, the light signal is converted back into electrical, and then using an appropriate transducer, we convert into original signal which was transmitted. So the optical detectors are classified, and we also evaluate on the basis of some parameters that this optical detector performs better than other optical detector. And there are some criteria upon which the classification and the quality of optical detector are based. Those attributes which are responsible in order to determine quality as well as classification of optical detectors are called as characteristics of optical detectors. So we know that in any optical detector, this is just you know uh, the optical detector. How does it work? It's just an explanation. You see here that this is the area where light is incident, and this incident light then excites the carriers, and those electrons which are emitted from the cathode, they are attracted by the anode, and those electrons then flow through the circuit and constitute an electrical current. So this is a normal working principle of the optical detector, in which the light energy, which is the incident photon here, rather bundle of photons here, is converted into electrical signal that flows from anode to cathode, or yeah, anode to cathode in the external circuit. So the classification, as I have told you in the beginning, that classification as well as performance of optical detectors, they are based on some parameters, some features, attributes called as characteristics. So this lecture is all about the important characteristics, the main characteristics of optical detector. The first one among the characteristic is 3 dB bandwidth. This 3 dB bandwidth is a very important term in any communication system, where we talk about the signal strength, the band of signals, the range of signals where the strength is appropriate, where the 3 dB, when we talk even about filter, signal processing circuit, low pass filter, high pass filter, or any type of filter, 3 dB bandwidth plays an important role. And there is a reason behind why it is called as 3 dB bandwidth. As we know that bandwidth in the optical detector will be actually the range of wavelengths, rather saying that it's a range of frequencies, it will be range of wavelengths which will be detected. The frequency where the detector output electrical power drops by 3 dB from the reference value is called as 3 dB bandwidth. That's different thing, but let's understand what is bandwidth here in optical detector. What is the concept of bandwidth here in optical detector? A bandwidth is, as I told you, range of wavelengths. We know that the light is characterized by certain range of wavelengths. So that wavelength will definitely correspond to some frequencies as well, because we know the velocity of light, and then we can determine the frequency as velocity of light divided by wavelength. So we can also say that it's a range of frequencies. And generally the bandwidth, in the usage terms, in any communication system, be it satellite, optical, or digital or analog communication system, bandwidth is always expressed in hertz, and then it is shown as the range of frequencies. So we can see here also you see here there is a response actually. This is called as response of uh, the amplifier, I'm sorry, response of detector, maybe photodiode or phototransistor. This is response, that this is how that the photodetector is responding to the optical input. So generally what do? We determine 3 dB bandwidth. And what is 3 dB bandwidth? Actually, you see here the bandwidth is extending from lower cutoff frequency to higher cutoff frequency. And these two frequencies are called as lower 3 dB frequency and higher 3 dB frequency. All right, and then the value or the range which is extending from lower to higher, this is what has been shown here, is called as bandwidth. Now, why it is 3 dB bandwidth? Because this lower cutoff frequency is 3 dB and higher cutoff frequency is also 3 dB frequency. So the bandwidth will be obviously called as 3 dB. And there is a reason that you see here, it's 3 dB below the low reference value. So the low reference value, say it's minimum 1. So when you convert into logarithm, it will be 0 dB. So this is 0 dB line, right? 0 dB line, and see here minus 3 dB. It means with respect to 0 dB, it's down by 3 dB. It's down by 3 dB. Actually, this is the standard way of defining 3 dB cutoff frequency. Sometimes we call it as RMS frequency also. Because when you find this value as a maximum value, say any maximum value, and you find out the value of the amplitude or the gain at this frequency, I will tell you this becomes 1 upon square root 2, which is 0.707 times maximum value. Now you remember 0.707 times something is called as RMS. So therefore, sometimes RMS lower cutoff frequency, RMS higher cutoff frequency, and the range is called as bandwidth. Sometimes the same frequency is called as half power frequency, because see, the amplitude becomes 0.707, that is 1 upon square root 2 times. When you calculate power, we know that the power is proportional to square of instantaneous value, and therefore it will be 1 by 2 of the maximum power. So sometimes we call the same thing as the half power bandwidth or half power frequency. So, but there is slight difference between optical 3 dB and then electrical, dB concept. In electrical, it is actually 6 dB, because original spectral response is plotted for an optical signal only. But when you actually convert into electrical response, you will find it as a 6 dB. All right, then there is a next one called as CMRR, another popular term, CMRR, which is called as common mode rejection ratio. Common mode rejection ratio, CMRR. It is generally expressed in dB. Why this is expressed in dB? Because when you take here, you see here how you are calculating CMRR. VCM divided by V balanced. It is common mode output divided by balanced output. That is common mode signal divided by balanced signal. Balanced signal may be a difference signal or the mixed output, the output of mixture, which is called as balanced signal. So this is a very popular term used in the operational amplifier, CMRR, right? Where we divide the common mode signal divided by the differential mode. So here in place of differential mode, we have balanced signal. So if you can see, it's like a gain factor, common mode voltage divided by balanced mode voltage. So in one way, it's voltage divided by voltage, and therefore it's what we can say that it's dimensionless quantity. It's unitless quantity. So when it is unitless quantity, we call it as, we use another term to express its unit, that is dB. And this is how it is expressed. It is computed in dB. 20 log of VCM divided by V balanced to the base 10. The base is 10 because desi is the term. There is natural logarithm also, but this is 10 logarithm. So it indicates how much noise rejection is there. That's very important. What is role of CMRR? What is role of CMRR in optical detector? That how much noise is suppressed, how much noise is rejected. See, the common mode is indicating the desired component, whereas the balanced component is actually indicating the noise, contribution. So when you see that the noise contribution is more, your CMRR will become less, and accordingly the dB value will also be less. So please remember, CMRR is always expected to be very high. CMRR always has to be very high in order to get large value of CMRR. Our value of balanced, the noise signal must be minimum. So this is second, what we call the characteristic. The third one is called as conversion gain. What is conversion gain? Now, what do we know about the optical detector? It converts some energy from one form to other. So this is why conversion gain comes into the picture as one of the important characteristics. So when see V by W, that is voltage per unit energy, per unit watt, say it's given. So conversion gain is generally written as the product of photodetector's responsivity, amplifier gain, and the input impedance. Can you see here? See, the conversion gain is equal to responsivity multiplied by amplifier's gain multiplied by input impedance of the receiver. So this is how we calculate. This also can be written as, that is R into Ri, where this Ri is actually can be written as, for an unamplified photodetector. Suppose there is no amplification, we can simply write R into Ri. For receiver, Ag is multiplied. For detector, see, when you are receiving the signal finally after passing through detector and then amplifying it and all that, right? So actually after passing through detector, we employ a number of amplifiers, series of amplifiers, so that the signal strength is very good. And this is why conversion gain for receiver is R into Ag, R multiplied by Rin, where Ag is the gain of amplifier, R is the responsivity, where Rin is the input impedance of the circuit. And when we are calculating it for detector, no amplification will be needed. So the output voltage here, how we can calculate the output voltage? This is nothing but the product of conversion gain and the optical input power. Gain multiplied by optical input power. We can calculate, the output voltage. And when we substitute the value of G here, we can write the expression of output voltage like this. So conversion gain means how much output is effectively output, and that output is depending on responsivity. More is the responsivity, more will be the output voltage. Gain of the amplifier, finally, when we are receiving through amplifier, must also be very high. Similarly, input impedance and the power input, optical power input. So you can understand in one way that if we are giving some particular output, that is input power, how much output it is generating. So it's called as conversion gain. Conversion gain means the optical input power, how much electrical output signal it is generating. So that is related with, that is termed as the conversion gain. More is the conversion gain, more will be the electrical output. So therefore conversion gain has to be very high. Next one is continuous wave saturation power and gain. What is this saturation power? The point at which the output of photodetector becomes non-linear. See, here is a linearity, here is non-linearity. So when it becomes non-linear, we get that saturation power. Because see, when it is, now how do we decide whether it is linear or non-linear? Because when we are saying that amplifier is used, so when we use amplifier, the optical input power increases. You can see in the previous expression, more is the optical input power, more will be the optical output voltage. So relationship is linear here. So the moment that linearity is lost, it becomes non-linear means what? Even if we now increase the optical input power, there is no increase in the output voltage. So we will call this situation as the saturation power, and then gain is nothing here but amplification. And there is another term related to gain, which is another significant factor in deciding the performance of optical detector, which is called as flatness of gain. Is it flat here? Yeah, you see here flat. You see there is no change. It's a constant over a range over this bandwidth. So this is the variation of gain over an entire bandwidth. And remember, if over the entire bandwidth, over the entire range of frequencies, if there is no change in the voltage gain, look at here dB versus frequency. So how much, what type of response we'll get? Flat response will get. And flat response means there is no variation, there is no change. So it indicates that it describes how much variation it has. And if it has variation, it will not be flat. If it doesn't have variation, it will be flat. If it has variation, no flat. If it does not have variation, it's flat. It means constant gain. In other words, we call it as stable gain. See, how much voltage gain you are getting, you are obtaining is definitely one decisive factor. But what is even more important is whether the gain which you are obtaining is stable or not. Stability is very important. So that stability is indicated by the flatness of the gain. So this is another parameter which is an important parameter in the optical detector. Next one is related to impulse response and optical power. Now you see what is impulse response? The width of photodetector's output in response to a first optical pulse, it is measured also as full width at half maximum. You see here, maximum is here. And what is full width half maximum? Look at here. Full width half maximum means half maximum is lying at x1 and in upper side x2. So this range is called as full width at half maximum. That is half of the maximum full width. This is called as impulse response. If you see in terms of power, this is the same concept, half power we are taking. When we calculate in terms of voltage or current or instantaneous value, it's RMS. But when you calculate in terms of power, it's half. Actually, the concept of bandwidth is 3 dB bandwidth. And 3 dB bandwidth itself means that the signal is lower by 3 dB from its maximum. And where it is 3 dB down, at these values, either at maximum, half of the maximum power, or RMS of the instantaneous value. So this is another important parameter. And since this response is called as impulse response, how well the response is, how widened the response is, how narrower the response is, it is governed by, it is indicated by the impulse response. And there is an important parameter. From impulse response, what do we get actually? From impulse response, we can determine the value of FWHN, which is also a decisive factor while choosing an optical detector for a specific application. Next is maximum optical power. Power at peak responsivity. Power at peak responsivity. Power at peak responsivity. When the responsivity is maximum, that value of power is maximal optical power, is maximum optical power. Beyond that, you cannot, because the responsibility means what? This is the ability to respond at optimum value. Beyond that, there will not be any response. For whatever optical input power, there is a capability that this much electrical output will only be produced. Beyond that, it cannot be produced. So that's the peak responsibility. And at peak responsibility, whatever is the power, that power is called as maximum optical power. Next term, which is an important term, called as NEP. What is NEP here? Noise equivalent power, NEP. This optical power or optical power which produces SNR of 1 in 1 hertz bandwidth, 1 dB in 1 hertz bandwidth, that minimum optical power which can be detected, that can equivalently produce 1 dB for 1 hertz bandwidth. It's the minimum value. That is called as NEP, noise equivalent power. And based on this noise equivalent power, we can calculate the minimum power, the minimum optical power we can calculate, which is NEP lambda, which is the function of lambda, right? Multiplied by square root of B. So you can also see more is the bandwidth, more amount of optical power, and more is NEP, more amount of optical power. All right, so where B is the entire measurement of bandwidth. So what is next? The next parameter is noise figure and output impedance. Noise figure and output impedance. This is also important part. Noise figure is actually a common term used in any communication system. Very common term. It indicates, the quality, rather quantity of noise, the amount of noise which has been added in the, or which has been mixed with the original signal. And of course, output impedance is another important factor that is very important to check, to verify whether impedance matching condition is there or not. So minimum input output required, minimum input output impedance requirement is everywhere in all transmission line in optical detector when it comes to connecting in the practical application. So noise figure, the amount of excess noise above 174 dBm in 1 hertz bandwidth, it's always defined with respect to 1 hertz. So in a 50 ohm system, 8 dB corresponds to input noise current of 22 picoampere per unit square root of hertz. This is how you quantify the value of noise figure. More is the noise figure, poorer is the system, worse is the system. And then optical input is of course a parameter. Optical input affects conversion gain. Optical input affects responsibility. Optical input affects the efficiency as well. So output impedance is generally 50 ohm to provide a proper impedance that can match the requirement of the application, the requirement of connecting the optical detector in the application. So that is noise figure. And what is the next? Output impedance. Next one is also interesting parameter called as, it is called as rise time and optical detectors. I mean, what is the role of rise time in optical detector? Rather, it's rise time in optical detector, right? So rise time is also an interesting factor whenever we are interested to analyze how much signal is growing, how the signal is rising, how the signal is changing, that the rise time plays a significant role. So here you can see that this actually is the standard definition of rise time. You can talk about control system, you can talk about signal processing, you can talk about circuit theory. Everywhere rise time is generally defined in two ways. Actually, see, in control system we have two types of system: underdamped and overdamped. So we define either 10 to 90% or 100% as well. So, but 10 to 90% is the standard one in the, especially when it is rising, because you do not know where the signal is becoming 100%. So we choose two values, two percentages of the maximum, that is 10% of maximum, 90% of maximum. So when the signal attains 10% of maximum, say here, and whenever it attains 90% of maximum here, so this actually difference is called as rise time. And that too, when it is in the rising side, it is called as rise time. When it is towards falling edge or falling time, it is also called as fall time, because the signal may be increasing, rising, or the signal may be decaying. So while decaying, the same terminology, that is from 90 to 10 is called as fall time, and from 10 to 90 during rising, during increasing mode of the signal, it is called as rise time. So rise time and then this fall time are also important factors, are also important parameters in deciding the, the quality of the optical detector which is used. So there is one more parameter called as photo detector diameter, the diameter of the photo detector area, active area, so that there is no compromise on bandwidth. That is, how much is the active area? You cannot increase the active area by beyond certain value, because you cannot compromise over the bandwidth. Bandwidth is not something which you can choose or which you can take any value. It is determined by a number of factors, cost, and there are many more things, that the capacity, the channel capacity, the data rate, and all that, when you apply optical detector in a particular application. So rise time and photo detector. Rise time is also defined in terms of 3 dB bandwidth. It is 35% of 1 by or reciprocal of 3 dB frequency. We can write rise time as 0.35 divided by f3 dB gives us rise time in the optical detector. Responsibility, we are talking about responsibility. What is responsibility? Is actually the amount of photo current that results from an optical input of 1 watt. 1 watt is, the standard value we are taking. So if 1 watt of input, optical power is given, how much current flows there, how much current it generates, is called as responsivity. I photon, where the photo current is equal to R responsivity multiplied by input power. So you can look at here, more is the input power, more is the current. And if more is the current, we can also say that, and when we consider 1 watt, so you can say for 1 watt of optical input power, it's same, that is photo current is equal to responsivity. So for a particular value of optical input power, more is the current, better is the responsivity. Is the ability to respond means better is the current, more is the current. Responsivity is wavelength dependent. See, it's depending on current, means it's depending on photons. And photons are nothing but bundle of photons actually constitutes light. So it depends on wavelength, and it is related to quantum efficiency also. We know that what is quantum efficiency, that how many electrons or how many carriers are released per incident photon. When there is an incident photon, how many electrons are generated, called as quantum efficiency. That is the term actually used in optical source. So quantum efficiency is actually R multiplied by H into N divided by E, where R is responsivity, H is Planck's constant, N is the number of electrons, E is the per incident photon. Right? So this is how the responsivity is also correlated with the quantum efficiency, where H is Planck's constant, N is the frequency of incident radiation, and E is the electron charge. The quantum efficiency value for maximum responsivity versus wavelength. All right. Next one is VSWR. VSWR, voltage standing wave ratio. Actually, this is also a term which is very important term in all transmission line, right? Whenever the signal is transmitting. So this is defined as ratio of maximum to input amplitude of a standing wave. In the subsequent lecture, we'll understand what the standing wave is. So it's whenever we get the standing wave, the ratio of maximum to minimum, and that occurs because of impedance mismatch at the end of transmission. So whenever there is a mismatch, a standing wave occurs, and the ratio of maximum to minimum will be termed as VSWR. So VSWR say it's 1 by 1 that indicates perfectly matched termination. And when there is no perfectly matched termination, VSWR will not be 1 by 1, will have different values. Next parameter is wavelength range, the range over which the photodetector operates smoothly. The range of wavelength, we are defining the bandwidth in terms of wavelength, in terms of frequency. So what's that range of wavelength over which the functioning, the operation of photodetector is smooth, it's proper. Below certain value, the photons, see, why we are talking about range? Below and above, both are not desirable. Why? Below certain value, the photons are absorbed outside the active region of photodetector. That decreases the photodetector's bandwidth, right? So if you go below, so some photons are absorbed outside the active region, and there is no need of, or there is no use of those photons. And when we go above certain value of wavelength, the photon energy is less than the semiconductor gap, and the photon is not absorbed by the photodetector. So that much energy will not be sufficient to overcome the band gap, and there will not be any photon absorbed by the photodetector, and then there is no use of that photon. So wavelength range is the range of wavelength over which the photodetector performs smoothly and in a proper way. So this is how, let's summarize this lecture. This lecture is all about the characteristics of optical detector. While choosing an optical detector, while evaluating the performance of optical detector, while classifying the optical detector, what are the factors, what are the characteristics which are responsible in the process. So those characteristics are called as optical characteristics or optical detector characteristics. So there are a number of optical characteristics, out of which we have discussed here the major characteristics like 3 dB bandwidth, CMRR, the responsivity, conversion gain, which are the important characteristics of any optical detector, which we have discussed here in this lecture. So that's all for this lecture. Thank you.